So today we're going to start chapter 6. This is section 6.1 and a little bit of 6.2, talking about probability distributions and how they're models of random experiments. So it feels like random events seem really unpredictable, but if we observe them long enough, often we'll see a pattern. And so we're going to be looking at how we can use that to make probability distributions. In previous chapters, we studied distributions for numerical and categorical variables. Um, this following distribution is the distribution of ages for the New England Patriots. And we're going to be focused on numerical variables. So let's just take a look. So we're seeing a histogram here, and we've got our counts over here, right? So for example, 22, people who are 22, New England Patriots who are 22, it looks like there are 8 of them. Okay, and we can talk about the shape, the center, and the spread. We're noticing here the shape is skewed to the right. So this distribution gives us the ages of the players on the team as well as the frequency. So right, so 20 players who are 22 years old, there are 8 of them. And we can read other frequencies off. For example, players who are 26, there are 25, there are 10 of them. Because, so here's 22, and then here's the players who are 25. Okay. So another way to show the same histogram is to show it in table form. And then we can ask other questions, like what proportion of the players are 22 years old? So we know altogether there are 79 players, and 8 of them are 22. So if we wanted to answer what proportion are 22, we're looking at 8 over 79, which is about equal to 10%. That's the same idea of asking, what's the probability of randomly selecting a player who is 22 years old, right? 8 out of 79. So the probability of selecting an age equaling 22, or maybe a little bit more mathematically using the variable x, if x is equal to a player's age in years. So what's the probability of selecting one that is 22? These are all equal to 8 out of 79. Just some different ways of saying it. So the distribution of the ages for players on the New England Patriots can be displayed using a relative frequency histogram. So this is the same histogram, but now we're looking at relative frequencies. That's over here. So you can already see just quickly that if we're looking at those 22-year-olds, the relative frequency is about 10%. That's what we calculated on the previous page. This is 8 out of 79. So it's figuring out the proportion of observations out of the total. So in this chapter, we're going to talk about the probability distribution, which tells us about possible outcomes of random experiments and the probability of that each of these will occur. So already we're starting to look at that because we just talked about this is the probability of selecting a 22-year-old is 8 out of 79, and you're able to see that here in our relative frequency graph. So if we consider selecting a player at random from the above distribution, then the relative frequencies give us the probabilities, okay, of selecting a player of a given age. So let's answer the following questions. What is the probability that a randomly selected player is 26 years old? So using our table here, our frequency table, here is 26 years old, here's our frequency, and actually we have our relative frequency given to us, so we can really read it right off of there, 0.1646, or about 16%, we could say. And this would correspond to our relative frequency graph up here, and that's this, the height of this bin up at the top. Okay, what is the probability that a randomly selected player is less than 26 years old? Okay, less than, we're talking about 25, 24, 23, 22. In other words, we'd have to sum up all of these players and divide by 79, or the same idea would just be to sum up these relative frequencies. So if we do that, probability that player is less than 26 is going to be equal to 0.101 plus 0.114 plus 0.114 plus 0.127, and this comes out to be 0.456. So again, and this would correspond on our graph up here to the summing up the heights of these bars here that are less than 26. What is the probability that a randomly selected player is greater than 26 years old? Again, we'd have to sum up. We could sum up some counts here and divide by the total number, 79, or we could, oops, I'm going to switch to blue so that they correspond, okay, or we could sum up our relative frequencies here, 27, all the way up to 38 we'd have to be talking about. There's one other way we can do this, because everything here, if we added up this whole table, if we added this all up, it would equal 1. We could use the fact that we know that to do 1 minus the probability that a player was less than 26, and also the probability that a player was 26, because we also had that one. And we would end up with 0.38. So multiple ways to calculate that one. And on here, we're talking about the heights of all of these bars being summed up. So a probability distribution is sometimes referred to as a probability distribution function, and there's that little abbreviation, the PDF. In chapter 1, we classified variables as numerical, right, like ages, or categorical, in binary. Did the coin land heads or tails? In this chapter, we're really focused on our numerical variables for this whole chapter. And we're going to be breaking numerical down into 2 more categories. So before we had variables, right? And we had numerical and categorical. And now we're looking at breaking down numerical into 2 categories, discrete and continuous. So we've already classified them as numerical, and now we're looking at 2 types of numerical. We've got discrete, which are like numbers that you would list or count, like the number of people waiting for a bus or something. There might be 1 person or 2 people or 5 people, but there's not going to be 1.2 people waiting for the bus. The other type of numerical variable is a continuous variable. They have numerical variables that can't be listed or counted. They occur over a range. If you think about weights of babies being born, they could be 15.45 ounces. If you had a more exact measuring scale, that'd be a pretty big baby. You could go out further. You can't list all the actual values, so they're continuous. And it's going to be very important for us to distinguish which one we're working with. We're today going to be focused on continuous. You can see that we'll be focused on discrete variables a little later on. So if the ages of the New England Patriots were reported as integers, but they would be considered discrete, but age can also be considered continuous because if ages are not rounded to the nearest year, then they can be lots of possible values like 26.01, 26.0009 years, depending on how exact it's being reported. The following diagram, this is straight from your textbook, kind of helps you visualize the two different types of numerical variables. Discrete is a staircase. This is like, I like to think of it as like the counting of like people, which is a good one, the number of people waiting, or the number of books at a library. You don't have partial ones. You either have one or two. Whereas continuous is like a ramp. You could be anywhere along there and you cannot list all the possibilities. Okay, so let's skip down here. The distinction between these two types of numerical variables is important because it determines how we can display their proper probability distributions. So a discrete variable can be displayed as either a graph or a table, right? Because we can list all of the values. But a continuous variable can be displayed as a graph, like a histogram, but not as a table where the values are listed. It has to be listed in a table form. It'll have a range of values. So on the next page, we're seeing a sample distribution of heights of a sample of mothers. Daughter, oh, sorry, I read the wrong thing. So this is the source of where it's from. These heights are considered continuous because the heights are not rounded to the nearest inch. Any of the following heights are possible. You could have you could be 62 inches tall, but they could have gone out further to 62.01 or even further when they were measuring these heights. So up top, we're noting that we have a relative frequency histogram. And below, we're seeing how this table would look. This distribution gives us the heights of women in the sample as well as the relative frequency. So notice that instead of listing the heights individually, we have ranges over here, or intervals. So this first row is giving us all the heights who are 55 inches to 60 inches, but probably not including 60 inches. 60 inches would be included in the next row. So we can see there's 194 women that were 55 to 60 out of the 1,375. And so that first row here, 194, this frequency, right, that would be 194 over 1375. We could see that up in the frequency histogram if we looked at the heights of all these bins here and added them up. Okay, so they would come out to be very similar. how do we find probabilities for continuous outcomes? So as we saw, we can't list all the possible values we might see, but we can list the range of values we might see. We can find a probability that a particular observation is between two given values. So use the histogram to find the probability that a randomly selected mother has a height between 60 and 65 inches. So let's look at where that would be on here. Try to fit it on. So between 60, oh, I thought I changed to red. Let's try that. Between 60 and 65. So we're talking about the heights of these bars here. Will give us the probability of observing a mother in there. So that's adding up 0.12, 0.15, 0.17, and that comes out to 0.71. If we look below, we can see that the table, the relative frequency table, matches what we just found. So if you create a table like this in StatCrunch, you don't have the ability to adjust these intervals. It is what it is. It gives you what it decides to split them up. But remember, in StatCrunch, you can adjust the width of these bins. So you can make your histogram match the table if you want to look at these two things. And so since we have just a 1 inch, we have the width of this is 1, the height of this is 0.12. One thing we can notice that the area of this bar here, area is equal to 0.12 times 1 is equal to 0.12. So the area of one of these bars is the probability of selecting a person who is 60 inches for that case. And finally, let's look at this last question. What's the sum of the relative frequencies in this histogram? So if we add up the entire histogram or this table, they add to 1 because it's a distribution of all the data. And we're working with the probability. So the probability of selecting a mother that's between 55 and 75 inches is 1. That's everybody's in that case. So let's look at one more example in this section. A coffee shop manager is interested in finding the probability that a customer will wait less than 2 minutes to be served. The following probability density curve is a model of the histogram of wait times for her customers. This probability density curve shows the probabilities for this continuous valued random experiment. So these are wait times in minutes, and it's a continuous value, okay? So it doesn't have to be 1 minute or 2 minutes. And a probability density curve, this is a model of the histogram. So we're looking at the model here, right? Not the actual data. And if we want to know the probability that a person's been waiting between 0 and 2 minutes, we're going to be looking at that area in here. So this is similar to what we were just talking about, that the area under this probability density curve, this whole area here is 1, okay? Area under and so we want to estimate what's this area here, because we only want to know what's the probability of waiting between 0 and 2 minutes. You can see that we don't really have a great way of doing this. Finding areas under curves like this would actually use calculus to do that, something we're not going to be doing. So here we're just going to be estimating that. It looks like the red area is a little bit less than 50%. So let's say maybe around 45% of the area of that whole curve. So if X is equal to wait time in minutes, then the probability of X being less than 2 looks to be about 0.45. Use the diagram to estimate the probability that a customer has to wait more than 2 minutes. Okay, so now we're talking about the other side here. More than 2 minutes, that's this area in here, right? And we just said that the whole area under there is 1 or 100%, right? So if we've guessed that it's about 45% or 0.45, the probability of having to wait less than 2 minutes, then the probability of waiting more must be about 55% because it's going to add up to 100. So in practice, it is often difficult to know the exact shape of a distribution. For instance, how did the coffee shop manager know that the probability density curve given was the right shape? It's probably based on data. The manager hopes this probability model represents a histogram of wait times, that they can't be completely sure. They could compare predictions from the model to actual frequencies and determine how good the model's predictions are. So that was a pretty fancy shape. If the wait times were uniformly distributed between, say, 1, 2, 4, then we could find the area. Like if we have a uniform distribution, right, and we want to know the probability of waiting between 1 and 2 minutes, this is a rectangle. So we can multiply 1, the width down here, times 0.25, the height, and find out the probability of waiting between 1 and 2 minutes is 25%. So when it's like something that we know how to find the area, it's easier. Up here, we were just guessing because we don't have a great way of finding the area of under this kind of curved shape. In the next section, we're going to talk about a model that's used often and how to find the area under the curve.